After introducing high-wash Sobolev spaces on arbitrary metric measure spaces, we decided that it will be nice to have some actual calculations done in the Euclidean space to get some idea of how they relate to the classical Sobolev functions. And in order to do that, we needed to familiarize ourselves with some very commonly known tools from analysis. The first such tool we introduced was the maximal function, and then we discussed how it gives a proof of the Lebesgue differentiation theorem. Recall that for any locally integrable function on any metric measure space, we can define the maximal function as the supremum over averages of all balls centered at x. There's also, by the way, notions of non-symmetric maximal functions where you only require that the point belong to the ball rather than be the center of the ball. We also have a truncated version of this where you put an upper bound on how big the radius you allow in that definition, and this truncated maximal function becomes useful also in certain situations. And of course, the probably only reason maximal function is good is because it is actually a bounded operator. Despite MF always being bigger than F, at least point-wise, the LP norm isn't too bad. So M defines a bounded LP to LP functional when P is bigger than 1, and there is a weak estimate for P equal 1 case, which some of the viewers, I thank them for finding the references, and it is called Chebyshev's inequality. Okay, so the new tool we want to introduce is what is called the Riesz potential of a function. So let's first define the Riesz potential for a function on Euclidean space. So suppose f going from Rn into R is locally integrable. Then we define, well, there are many Riesz potentials, but the one we're talking about is denoted often by I1 of f or just IF if you never talk about other exponents alpha in place of this one. So to evaluate this function I1f at x, what you do is you integrate the function f of y, which you can because it's locally integrable, against the kernel x. Remember, x is our fixed point where we want to evaluate the function, and y is our integration parameter, and here is n minus 1. So if you had alpha, it would be n minus alpha. So this is the Riesz potential or Riesz potential of order 1, and you will do this integration over all Rn. So y is here and here, you integrate against it, and you get a value depending on x, which appears here, and that becomes your newly defined function. So pictorially, you have fixed your x, and for example, easier ways to deal with such integrals, say if f is constant, is to do them in polar coordinates, because you take fixed radius around x, and the denominator becomes a fixed constant r, and then you let r change. So polar coordinates, we will see a lot of this calculation when we actually try to prove estimates for high-wash class. So we see that so this kernel, so this is really convolution against the so-called Riesz kernel, x minus y to power n minus 1. This blows up to infinity if y approaches x. So this operator intuitively will emphasize singularities around x. So if function fy is, say, near infinity around this particular x, this will be even worse because it will be helped by this factor. But remember, f itself is locally integrable, so for example, if f is completely integrable, say in LP, then this cannot happen at many points, just like in maximal function thing. So that's why for integrable functions, despite visually having this singularity, the I1f function cannot be large everywhere. And also notice that if y, x minus y, is bigger than 1, actually the denominator is making the function even smaller. Another big difference with maximal function here is that we don't have absolute value here. It's the function itself. So this can produce negative values as well as positive values. In subsequent videos, again, when we try to relate classical Sobolev functions to high-wash Sobolev functions, we will see why on earth someone ends up in this place with this denominator. But again, so when you first see this thing, it looks very strange, very scary with that singularity at the point x. But the measure theory and the magic of integration is that we only look at things in an average sense. A function can be infinity at some point, at many points, still be integrable. So here is the main theorem about Riesz potential. Again, I am following lectures on analysis on metric spaces by Juha Heinonen. So this operator, the theorem reads that the operator which takes f to I1 of f maps, okay, now I notice that here this is applied to absolute value of f. I don't know why, because, well, I1 of absolute value of f is bigger than I1 of f itself. So if this is bounded, that one should also be bounded. But let me be safe and just follow the statement here. So this operator is bounded from LP to, okay, so this is even better than the maximal function. So LP goes to LP, but here it goes actually to an even more integrable space, NP over n minus p, which you probably recognize as the Sobolev exponent. When p is in the range 1 and n, and not including 1, then this is bounded from here to here. So the remark is that np over n minus p is often actually bigger than p. And notice that if p is closer to n, this is almost infinity, so you almost get a bounded function. So there's even a stronger boundedness compared to LP to LP. And the relevance for this exponent, the significance of this is that actually the Riesz operator, the Riesz potential applied to the gradient, so when we have gradient instead of the function f itself, will be used and can be used to prove Sobolev embedding theorem for this range of p. And there is the second part to this, similar to maximal function. So p equal 1, we have some weak boundedness results. So we have weak Ln over m minus 1, so which is just np over m minus p when p is equal to 1. So weak ln over n minus 1 bounds. Precisely. So what do we mean by weak? So L1 functions do not necessarily map to ln over n minus 1 functions, but so the set of values where I1 of this absolute value of f is bigger than a t, so for every t positive, the measure, the Beck measure of this set times, so n over m minus 1. So this is as if we are talking about integral of this functional to power n over n minus 1. So compare it to this. So the value of the function to power n over n minus 1 times this. So this set, which is almost like the n over n minus 1 integral of that, will be no larger than some constant, which only depends on the dimension n, times the L1 norm of f. So this will be L1 norm of f to the power n over n minus 1. So this power here doesn't matter. So this is just saying that the L1 norm of the function almost gives a bound on the n over n minus 1 integral of the function. So this is the weak type estimate corresponding again to the case of p equal 1 of the maximal function. So interestingly, the proof called by Heinonen as elegant, given in this book, but not due to Heinonen, uses the maximal function theorem. So to prove this boundedness theorem, we actually use some estimate of this type. So let's say proof ingredient, and a very useful inequality in itself is that the Riesz potential of f at every point x is bounded by some constant which depends only on n and p. The LP norm of f to a certain power, which is p over n, times the maximal function of f evaluated at x, and this maximal function to the power of 1 minus p over n. Again, for the proof, the full proof of this theorem, go to this book. But yes, so once you have such an estimate and you know the maximal function theorem, the LP boundedness of MF, from that you get LP, or, well, because of these powers, you get NP over n minus p, which will probably take care of this one. Yeah, exactly. So if you know LP boundedness of MF, then you get a bound on NP over n minus p norm of the Riesz potential. Great. So Riesz potential is from harmonic analysis per se, and as you can see, the statement doesn't require any notion of derivatives or Sobolev functions. These are tools used in Sobolev theory, but in their own right, they are very useful in all of analysis and harmonic analysis. So with this, we wrap up our discussion of what is known as zero order calculus, on metric or metric measure spaces. And what is a zero order calculus? Is calculus without any notion of derivative. For maximal function, we have a function and we produce by taking supreme over averages a new function, and then we showed that it's LP to LP. Remember that it was true in doubling measure spaces. And now we have this other operator, the Riesz potential of the function. And again, we have this boundedness result. And these notions do not require any notion of derivative, any notion of Sobolev functions or anything. That's why they are called zero-order calculus. And before the development of Sobolev spaces on metric measure spaces, these had already been influential and had big applications. The one thing I must mention, though, is how do you even define this Riesz potential on a general metric measure space? So the claim, the boundedness claim that I had there is pretty much still true in a metric measure space. For example, you require that the measure of balls of radius r have this lower bound in terms of some constant r to power s. So such assumptions on the measure will give us the same type of boundedness of Riesz potential theorem that you see here. But what is the definition? Well, it's often very tricky to extend some notion from Euclidean space to general metric measure space because, well, for example, radius of a ball. So is r the radius of the ball, or is it the measure of the ball to power 1 over n? So in a Euclidean space, they become the same. But when you generalize to a metric space, is the r here really the radius or the measure to a certain power? And in the case of Riesz potential, it turns out that the right definition, so if f is a real valued function on a general metric measure space, what you do then to define the Riesz potential of order 1 of f at x is you integrate over x, obviously. Remember, we integrated the function over, so this will be integration, over this x minus y to power n minus 1. So it turns out that the right notion here will be that we will have distance of x to y. So we freeze, x is frozen, we change y on the space. So every y has a distance to x. And then we look at the ball centered at x of radius dxy. And then we take its measure. Okay? So this is just integration d mu, but this is an honest evaluation of the measure on the ball. How much is the measure of the ball? And in a doubling space, for example, we have assumed that the measure of the balls is non-zero, so this makes sense. So in the Euclidean space, remember that dx minus y is just x minus y. And this is, by the way, the notation Heinonen follows, because it's common notation that even in a metric space, if there is no confusion, instead of writing distance of xy, you just write this, although x minus y doesn't make sense. Anyway, so in the Euclidean space, distance x minus y is this, and the measure of a ball of radius, this is some constant, the radius to power n, which after cancellation gives you the n minus 1 part. Okay, so my pencil is dead. So this turns out to be the right definition of the Riesz potential on a metric measure space. And again, there is the theorem 322 in Heinonen's book, which gives you sufficient conditions where this still gives you a bounded operated. So certainly the measure is assumed to be doubling. As I said, it makes the definition even safer by not having 0 in the denominator. And also we have this lower bound on how the measure grows. So the measure of balls of radius r is bounded from below by power s of r. Okay, so now we have this 0 order calculus in our hand, and in next video we will return to Hawash-Sobolev functions in Euclidean space and use these estimates to see why given a classical Sobolev function we can produce a Hawash gradient for it. Until then, have a great one, and thanks.